Hi, welcome back. We're up to Lecture 7, Segment 2, and the topic of Lecture 7 is Intro to Regression. In this second segment, we're going to talk about how the regression coefficients are estimated. So I'm going to dive right in here. I'm not dividing this segment up into different sections or pointing out specific topics because there's just this one topic. There's a regression equation, and how do we estimate the coefficients in the equation? It's pretty simple because at this point we're just dealing with simple regression. Next week in the lecture on multiple regression, this gets much more difficult and requires matrix algebra. So I'll give you a little lesson in matrix algebra as we go into multiple regression. But this segment, still pretty easy. So here's the regression equation. I can rewrite it as a function of the predicted score y. And now I just have to estimate the regression constant and the slope. The key concept here, and the math is really easy. There's actually hardly any new math. If you remember how to calculate the correlation coefficient, that's basically the math. But there's a really important new concept right here. And that is that the values of the coefficients, and this is true for multiple regression, are estimated such that the regression model yields optimal predictions. Another way to say that is minimize the residuals. That's sort of the mantra of regression. Minimize the residuals. Minimize prediction error. This is known in statistics as ordinary least squares estimation, and is a very important concept that you should be very familiar with, or familiarize yourself with if you're not familiar with it yet. And again, the idea is just to minimize the residuals. The way we're going to do that is calculate our residuals. So that's right here, right? A residual is just the observed score minus the predicted score. We're going to square all of those to get rid of the problem of sign, right? Because some I'm going to underpredict, some I'm going to overpredict. So let's square them all and then sum them, and I get sum of squares, just like back in summary statistics when we calculated variance. Right? So we'll have a sum of squared residuals, and we want to minimize that value. And you saw that, or you've seen that now repeatedly, starting with our discussion of correlations, when we put this regression line into a scatter plot, right? The regression line goes through the plot so that it minimizes the overall distance between the line and those dots, right? The regression line doesn't go, say, up here, it doesn't go down here. It tries to minimize the overall distance between the line and each individual dot. That's the idea of minimizing the residuals. A slightly different way to think about this is to think about all the variance in y and all the variance in x, and then the covariance between them. And I'm going to try and illustrate this point through Venn diagrams because it makes a nice connection back to our calculation of the correlation coefficient and the idea of sum of cross products. So let's bear with me if you don't like Venn diagrams. If you like Venn diagrams like me, you're going to enjoy this segment. So let's look at some Venn diagrams. So imagine I could represent the sum of squares for y in this one circle or Venn diagram. I have some variance in y. Likewise, I have some variance in x. And we did this when we talked about correlation. The overlap between the variance in y and the variance in x is the sum of cross products between x and y. So the degree to which x and y correlate is going to be represented by the degree to which these two circles, ss.y and ss.x, overlap. Right? So high degree of overlap, we're going to get a correlation approaching 1. No overlap, we're going to get a correlation approaching 0. Now that we're in regression, I'm going to change the notation a little bit. And now this overlap I'm going to refer to as sums of squares for the model. So this is the model sums of squares. You can think of this as the explained or systematic variance in y that's explained by x. So again, how can we think about sum of the squares residual? Well, it's just what's left over in y. So it's the unexplained variance in y. So here where we're doing just a simple regression, this is easy. We just have some of the variance in y is explained by the model, some of it is unexplained, that's the residual. And again, the goal is to minimize the residual. So the formula in simple regression is very easy. If we calculate the correlation coefficient, which we did last week in the lecture on correlation, then we just have to multiply by the standard deviation of y over the standard deviation of x. And the reason we need to do that is we need to take into account the scale of y and the scale of x. So imagine that there's a lot more variability or a much bigger scale in y than there is in x. Then a 1 unit increase in x is going to be associated with a large change in y, right? So that would take the correlation coefficient and inflate it, okay? So we have to take into account the standard deviation in both y and x to get the unstandardized regression coefficient b1. If we wanted to standardize the regression coefficient, which we will do, and we'll do it in lab this week, it's very simple in R, there's just one extra function. That's even easier, because if everything's standardized, then the standard deviation for y and the standard deviation for x are both going to be 1, right? If I put everything into z-scores, then the mean is 0 and the standard deviation is 1. Well, now look at the formula. It's just the correlation coefficient times 1 over 1, so it's just the correlation coefficient. So the standardized regression coefficient, and I'll use beta to signify the standardized regression coefficient, is equal to the correlation coefficient. Now that's only true in simple regression with just one predictor. Next week, all bets are off. When we get into multiple regression, it gets much more complicated. But for now, let's enjoy the simplicity. So to wrap up this segment, the important concepts to take away, again, are to understand the regression equation and the model. Perhaps the most important concept in this segment is the idea of ordinary least squares estimation, the idea that we're going to minimize the residuals in our regression model. And then understand that we can calculate both unstandardized regression coefficients and standardized regression coefficients. And I'll show you how to do each of those in lab this week using the LM function and one extra function to do the standardized piece. And that's it for calculating the coefficients.